Okay, in this problem we have two guys that are putting shingles on a roof, and so the roof is pitched at 25 degrees, and you are sitting at the very top of the roof when Peter, who is at the edge of the roof directly below you, 5 meters away, asks for the box of nails. Rather than carry it over, you decide to give the box a push and have it slide down to him. And if the coefficient of kinetic friction between the box and the roof is 0.55, with what speed should you push the box to have it gently come to rest right at the edge of the roof? Okay, so if I were going to draw this, I would probably draw a house that looks like this. And I would have me sitting up here, so kind of like me, and then kind of like this. All right, and I would have my box of nails right there. And then what's going to happen is I'm going to slide them down, and they're going to get right to, say, here. Right, so they're going to go from there down to there. All right, so I'm going to draw the picture a little differently. I'm going to make it look just this part of it. So I'm going to draw, let's see, I'm going to draw this. So starting here and ending there. That, and this is going to be my theta. I'm going to draw my boundary. So I've got, let's see, the force of the normal here. I've got the force of gravity. It's going to be from the middle, like that. And I'm also going to have force of friction, which is going to be, since it's going to be moving down the roof, it's going to be opposite the motion, so the force of friction. And I think that's it. So let's convert that to a free body diagram. So with my free body diagram, when I rotate the coordinate systems, I like to keep that angle so I can figure out the angle of the normal. So I want to make sure the normal, this is the force of the normal, it's perpendicular to my surface. And then my force of gravity is down like this. This is my theta here. So if that's that theta, then I know that this is going to be my theta. I'm going to move the force of gravity out of the way. So this is my force of gravity. And this is going to be my right angle. Okay, so this here is, if this is my theta, then I know that this is, so this is my y direction. Down the roof is my positive x direction. So this is going to be my force of gravity in the x direction. It's down that way. And then this is going to be my force of gravity in the y direction. Okay, so I know that this goes this way, and I know that this goes this way down. Okay, so let's look at our givens and finds. So we're given our theta is equal to 25 degrees. That doesn't even look like 25 degrees. Let me fix that. 25 degrees. Our mass is equal to 2.5 kilograms. Our x final is equal to 5 meters. Our mu k, kinetic friction, is equal to 0.55. And we want to find our starting speed, so v initial. Okay, so we're going to take our free body diagram and we're going to use that to create our Newton's second law equations. So let's do, oh, and I've forgotten one of my forces up here. So I need my force of friction. Okay, so if I do my forces in the x direction, some of the forces in the x direction equals, well, I know my box of nails is going to move down the roof, and I know it's going to slow down because I want to have it have a certain speed so that it stops at the end. So I know then I must have an acceleration, and I will have an acceleration up. So I'm expecting that the force of friction is going to be bigger than my force of gravity in the x direction. So my force of gravity in the x direction is Fgx. That's positive because it's going down the hill, down the roof, minus the force of friction is equal to ma. And remember, so my Fgx here is opposite theta. So I'm going to say that this is Fg sine theta minus force of friction is always mu k for moving, and then force of the normal is equal to ma. Okay, so let's worry about our force of the normal. So the force of the normal here is a little bit different. We can't just say it's Fg. And how do we tell what it is? Well, the sum of the forces in the y direction are equal to, so the box of nails isn't leaving the roof, it's staying at y equals 0. So since it's not moving in the y direction, we're going to set it equal to 0. And now the force of the normal is in the positive y direction, and the Fgy, so minus Fgy, that's the component of gravity in the y direction, and it's negative because it's down, because my Fg is down. So that's equal to 0. So force of the normal, I add Fgy to both sides, so I get Fgy. Since it's down here, this side, Fgy, is adjacent to theta, so that means I'm going to use cosine. So force of the normal is equal to Fg cosine theta. And so then the force of the normal is equal to mg cosine theta. And that's what I'm going to plug in over here. So I'm going to have Fg, and I know Fg is mg sine theta minus mu k mg cosine theta is equal to ma. All of my m's cancel. They're in all three components there, and I'm looking for v, so I really am trying to solve for a. So a is equal to g. I can factor the g out of the sine theta minus mu k cosine theta. Now when I plug in, I get a is equal to 9.8 meters per second squared times sine of 25 degrees minus mu k is 0.55 times cosine of 25 degrees. And when I plug that all in, I get a is equal to negative 0.74 meters per second squared. And that makes sense. So that means that my net force here is, so my F net is that way. F net is up. And that means my acceleration is up. So my box is moving down, but my acceleration is up because it's slowing down. So I'm going to use the equation for velocity. So I'm going to say v, so v final squared is equal to v initial squared. And I'm going to say minus 2a delta x. And that's because I know this is slowing down. So I'm not going to plug in a negative here. I already have the negative here. I know that a has to be opposite the velocity in order to get to like v final is equal to 0. So I'm looking for this v initial. This is what I'm solving for. So v initial is equal to squared is equal to 2a delta x. So vi is equal to the square root of 2a delta x. And like I said, I'm using the absolute value. I'm using the positive value. So vi is equal to 2 times 0.74 meters per second squared times 5 meters. So it's 5 meters down the roof. line there. And so VI then is equal to 2.7 meters per second. And that's what the box of nails has to start with in order to get just to the edge and stop before it goes over.